Okay, we are going to take a look at Lewis structures now. And really, in order to understand Lewis structures, we're going to do a little bit more than just the stuff in Chapter 7. We're actually going to look at some of the stuff in Chapter 7 and Chapter 8. But I want to start with just the basics of a Lewis structure. What exactly do we use? Well, we use a symbol for the element, such as the element O. And for every valence electron that is there, I am going to write one dot. Now, oxygen is in group 16. All of the elements in group 16 are going to have 6 valence electrons. So I'm going to put the 6 valence electrons here. Now, for the valence electrons, I'm going to start with 4 locations that I place them. All right, top, right, left, and bottom. Okay, so if I only have 4, I'm going to have 4 of these shown as such. Now, as I go past 4, I'm going to start pairing them up. And it doesn't matter really where you put the pairs, but it will help if you start putting them, if you have 2 pairs, put them adjacent to each other. That'll help us with some other things later on. So this is the Lewis structure for oxygen. And if I want to take and make water, okay, I'm going to add a hydrogen to it, right? So if I add a hydrogen to it and it's got 1 electron here, and I've got another hydrogen and it's got 1 electron here, they can share these electrons and we can show that. Now we don't necessarily have to put the dots in order to figure this out. We can show this, okay? Now, in addition to single bonds, sometimes we can share more than 1 pair of electrons. But let's start by looking exactly what does it mean to share a pair of electrons. Now, if I take a look at 2 hydrogen atoms, I'm going to have a nucleus for each of them and an electron cloud. Now, as those electron clouds come closer together, I'm going to have an overlap of them. Okay, so there's going to be an overlap here and an overlap here. And really, they're going to blend into one large overlapping orbital. Okay, this is what it's going to be like. Now, there. Notice this is shape, and notice also I'm a really bad artist, but you get the idea. Okay, but what if I have something else like carbon? Okay, carbon is going to bond with hydrogen to give us CH4. But when I look at the electron configuration for carbon, I'm going to find, well, we'll skip the 1s because that's a shielding layer. But in the 2s, I've got 2 electrons. In the 2p, I've got 2 electrons. Well, I can take and show one of these in the 2p, but according to this, one of these bonds should be different. Okay, I should have 1 that's formed from a 2s orbital and 3 that are formed from 2p orbitals. But in reality, all of the bonds in this particular one are identical to each other, showing us that something else happens. And according to something called valence bond theory, now valence bond theory we don't see until chapter 8, but according to valence bond theory, what happens is we have a sharing of these electrons. And overall, these 3 orbitals that are in the p and the one that's in the s combine together to form what we call sp3 orbitals. Now, where did we get that? Because we combined 1 s and 3 p's, sp3, okay? This is an sp3 orbital, and I'm going to kind of draw a very bad diagram of it. So here's our carbon nuclei. It's barely small, you can barely see it. And I'm just going to draw one of the orbitals. Now, in sp3 orbital, we need to understand we're taking an s orbital and a p orbital. And remember when we were talking about light, we talked about interference. And this is going to interfere with this in such a way that one of the lobes is going to be destructively interfered, and one of the lobes is going to be constructively interfered. And we're going to get something that looks something like that. And I know you think, that kind of looks like a fish. Okay, I'm not a very good artist, but you get the idea. Now, if we rotate this way, we will get the 3-dimensional shape of this sp3 orbital. Now, I'm not going to try to draw all the sp3 orbitals, but remember, this is our carbon atom, and over here, I have a hydrogen atom. This is how we have a bond between carbon and hydrogen. This is our orbital overlap that combines these together to give us our bond. So the 4 bonds in methane are all identical, okay? We'll even look at the shape of that a little bit later on. But in order to understand a little bit more, sometimes when we have something like oxygen, Okay. When I look at oxygen, I've got the 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I need to make a bond here. But atoms are going to be more stable if they can combine in a structure that gives them a filled outer shell. We call that an octet. Now, a lot of times we like to personify atoms and say they're going to be happy if they have a full octet. We have a happy molecule. Okay, well, that's not really true, but it still is kind of fun to do that. What we're referring to is atoms that combine to form bonds, and that is the lowest energy state. So it's important to understand that energy state is what we're looking for, that low energy state. Sure, we can talk about them being happy, but these atoms are not showing emotions. They're doing this because they're more stable in this configuration. But the question is, how do I form a double bond? Well, let's go back and let's look at our two nuclei. And for oxygen, we have in the 2s and the 2p. Okay, I'll get something like that. How am I going to overlap these in order to show this? Well, I'm going to have one overlap that occurs directly between the two. But in order to get my other bond, I am going to have orbitals that are not hybrid orbitals. So let's draw two just regular p orbitals, and we'll put them on the z-axis. Okay, if you can see colors, that's I drew those in purple p orbitals. Help us remember that a little bit. And what happens is these two are going to form a double overlap. Okay, so I'm going to have a single orbital that overlaps here. So our drawing here, I have the hybrid orbitals. Oops, again, as I said, I am not a great artist. I can do better than that, though. Okay, I've got my double overlap, and then I'm going to have my p orbitals that have the double overlap. Now, this is an overlap of one orbital from this atom and one orbital from this atom. This bond is an overlap of one orbital from this atom and one orbital from this atom. So I have two bonds here, even though I have three areas of overlap. There's only two bonds. Now, we refer to a bond which we have overlapping directly between the atoms as a sigma bond, the Greek single sigma. And pi bond is the name we give to the double overlap, which forms from pi orbitals. Okay. And this one, because one of our p orbitals here did not form hybrid orbitals, we have the hybrid orbitals formed between an s and two p's. So we call it sp2. Real creative naming, isn't it? But that's what we're doing. Okay. And if you're wondering, can I put a third bond in here? Yes, I can. Now it's going to be very difficult to draw because I have to actually bring it out of the board and back behind the board. It goes in the plane that's perpendicular to the board. That's where a third pi bond is going to go. No, I cannot get a fourth bond. Okay, I cannot get a third pi bond here. There is a way actually to get a fourth bond, and that has been shown fairly recently, like in the last 20 years, that there is such as a delta bond, which is an overlap of d orbitals. We're not going to look at that at all. That's a little bit beyond what we're going to look at in this class. But the important thing is that we can have single bonds, we can have double bonds, we can have triple bonds, and we can even describe the blending of those orbitals in terms of hybrid orbitals. We'll talk a little bit more about that when we get to chapter 8. Okay. So let's look at a couple more things. Okay. So we often want to decide by inspection how many bonds we're going to have to place there. But there's actually a simple calculation that we can do. Now, this calculation is based on something called the octet rule. That means everything is more stable if it has a full outer shell. Now, hydrogen does not have 8 electrons in its outer shell. When hydrogen has a filled outer shell, that means the 1s orbital is filled, it has 2 electrons in its outer shell. So for every hydrogen that has a full outer shell, it will have 2 electrons. So I want to look at something, okay? Let's look at this one. And I know you're thinking, oh, hey, that's salty, that's seawater, right? No, that's not what we're referring to. This is a substance called formaldehyde. And what I want to look at is the bonding that is present here. And I need to know how many bonds I'm going to put in here and what's going to be put together where. Now, the first rule we're going to follow is the least electronegative atom is going to be placed in the middle, with the caveat that hydrogen is never in the middle. Okay, so occasionally on some of the more advanced structures, hydrogen will be in the middle. But for the simple structures we're going to look at for Gen Chem 1, hydrogen is never in the middle. So lowest electronegativity is in the middle. Hydrogen is never in the middle. And if we remember our electronegativity table, oxygen had an electronegativity of 3.5. Carbon was down here at 2.5, so it's the least electronegative. A not really rule, but something that almost always happens. Carbon is almost always in the middle. See? So we're going to put that there. And we're going to put just around anywhere. We'll worry about whether we have the correct shape later. We're just going to put these other atoms there. Okay? And let's see what happens when we do this. Okay? Well, let's do a simple calculation. In order to have a full octet with carbon, I need to have a total of 8 electrons. In order to have a full octet with hydrogen, I need to have 2 electrons, but there's 2 of them, so 2 times 2. And in order to have a full octet for oxygen, I need 8. Okay, so this calculation is going to give me the number of electrons that would be needed if I just made everything with a full outer shell. Okay, so we're going to say 8 and 8 is 16 plus 4 is 20. So there are 20 needed. But how many valence electrons are actually present? Well, if we look at carbon, with the group that it's in, it's going to have 4. Each hydrogen is going to have 1, but there's 2 of them. Okay, I can draw better than that. And each oxygen is going to have 6. So 6 plus 4 is 10, 11, 12. There are 12 present. And if I subtract those numbers, I will get the number of electrons that need to be shared. Now, this number that I have here, this number is important because that's also the number of electrons I need to show in my Lewis structure. Okay, so let's look. 12 present, so 8 shared. Well, if we look, a bond is a pair of electrons. So I'm going to start by just placing a bond between each of these. Now, if I look, hydrogen is filled, this hydrogen is filled. So in order to get my other bond, I am going to place it here. So I now have 2, 4, 6, 8 electrons shared. And then with my remaining electrons, 8 are shared, there should be 12 present. I need 4 more. What doesn't have a full octet? Well, the hydrogens obviously have a duet to be able to be filled. So both of the hydrogens are filled. 1 bond fills a hydrogen atom. The carbon, 1, 2, 3, 4. Carbon has 4 bonds. That's 8 electrons. That's a full octet. Oxygen has 2 bonds to it. That's 4 electrons, and it's missing. And what do you know? I need to put 4 more electrons there. So let's go 1, 2, 3, 4. And now I have a full octet with everything. Now again, this calculation is based on the octet rule. Now the octet rule might be better stated as an octet guideline, but we're going to call it the octet rule. A little bit later, we will look at a whole bunch of things that violate the octet rule, that don't follow that. But for the moment, sticking with things that show a following of the octet rule, we can do an easy calculation and determine the number of bonds that we're going to have present.